Hello. In the previous lecture, we have introduced the concept of a wave function, which replaces the classical description of a particle in terms of its position and momentum. We now have to use the wave function, which is a function of coordinate and time. The wave function is spread over the space, and the wave function has two aspects: the measurable and the unmeasurable aspect. The measurable aspect of the wave function is its modulus squared, which gives you the probability to find the particle near a given point at a given moment of time. Actually, it is the probability density to find the particle. And the unmeasurable aspect of the wave function is the phase of the wave function. We have also discussed the importance of the stationary states in which the probability density associated with the wave function does not change in time, which also implies that the phase of the wave function is a linear function of time. It increases linearly as omega times some angular frequency times t, and that angular frequency is related to the energy in the stationary state as energy divided by Planck's constant, reduced Planck's constant. Now, the description in terms of the wave function would be useless unless we have a tool to calculate the wave function for any specific system. And this tool has been developed about 100 years ago by an Austrian physicist, Erwin Schrödinger, and it is now called Schrödinger's equation. In this lecture, I will not really derive, but motivate physically Schrödinger's equation for a simplest case where the particle is free. It just exists in space. It doesn't feel any potential. It doesn't feel any force. It is a free particle. And in the next lecture, I will make Schrödinger's equation more general and include the potential. So these are the topics that we will cover. I will start not with the equation, but with the solution, with the expected solution of Schrödinger's equation, which is the plane wave. And then I will try and construct an equation following Schrödinger's steps, try and construct a differential equation which has this plane wave solution as one of its solution. And finally, I will formulate Schrödinger's equation for a free particle, and we will also discuss a little bit again the concept of a measurement. All right, so what is a free particle? No potential, no force, and a free particle is the wave function of a free particle is delocalized. The free particle can find itself anywhere with equal probability. In terms of the wave function, this delocalization means that the modulus squared of the wave function is constant everywhere. So, but when I try and determine the position of the wave function, the position of the particle, I do get some number. The particle is here. Now, in order to determine the position of a particle, I need to perform an experiment. For example, I can insert a photographic plate, and when the particle hits the photographic plate, it leaves a mark, a bright dot on the plate. This is called a measurement. Now, there is a misconception about the procedure of measurement in quantum mechanics. So the common sense suggests that a measurement is performed by an experimentalist. So there is some conscientious being which designs an experiment and performs that measurement. In quantum mechanics, measurement is not understood in this sense. It is simply a process, an interaction of a quantum system, for example, an electron, with a classical system. Now, by classical, I mean that the system is so big that it is described by the laws of classical physics, such as Newtonian equations of motion, to a high accuracy. Classical physics is a limiting case of quantum physics. Quantum theory is more fundamental than classical theory. you can say that classical theory follows from quantum mechanics in the limit of Planck's constant goes to 0. So quantum laws apply to everything, but at the macroscopic level, for big systems, quantum laws can be approximated with the classical laws, like with the 3 Newton's laws, for example. All right. So a measurement. A measurement is an act of interaction between a classical and a quantum system in which some change happens in the classical system. And that change allows us to draw conclusions about the quantum system. So no need for an observer, for a being which is endowed with consciousness, which is simple classical system, quantum system, and they interact. That's the measurement. When a measurement happens, the wave function of the quantum system collapses to a particular state. So, for example, an electron, which was initially free, initially spread out uniformly in space, its wave function was spread out uniformly, collapses to a single dot on the photographic plate. Previously, we said that the modulus squared of the wave function gives you the probability density to find an electron near a particular point in space. Now, the probability density for the wave function to collapse to a given point of space is exactly this, modulus squared of the wave function multiplied with a small volume around this point of space. Now, if, let's say, an electron occupies a finite volume, so it is large and finite volume L cubed, so cube side length L, then modulus squared of the wave function is 1 divided by the volume. So the probability to find an electron near a particular point of space, R, is the volume, dV, small volume around that point, divided by the total volume available to the electron. All right. So now let's formulate the solution, the expected solution of the Schrödinger's equation, which we do not have yet, for a free electron, or any particle. But I will be talking about electrons for the sake of definiteness. It is a plane wave. From the theory of mechanical waves, we know that a plane wave is described by a function like cosine k r minus omega t, where k is the wave vector and r is the radius vector at a particular point in space. Or you can write sine kr minus omega t, or any linear combination of sine and cosine of kr minus omega t. These expressions cannot be the wave functions of an electron which is spread uniformly in space, which because they do not give equal probability density in space. For example, if we take cos kr minus omega t, then probability density will be cos squared of kr minus omega t, and cos squared has minima and maxima. So there are positions where the probability density has the highest value, cos squared equals 1, and the lowest value where cos squared equals 0. But we said that a free particle has the probability density uniform, position independent. So in order to get a position independent probability density, we combine cos and sine of kr minus omega t using Euler's formula. Remember that exponential to the power I theta is cos theta plus I sine theta. So the expected plane wave solution of the Schrödinger's equation, which we will construct today, is exponential to the power I kr minus omega t, multiplied with some constant a, which is the normalization constant of the wave function. Now, exponential to the power I kr minus omega t has modulus squared 1, because exponential to the power I theta has the modulus squared given by e to the I theta times e to the negative I theta, which is e to the power 0, which is 1. Now let's talk about this normalization constant. If we immediately say that the electron finds itself in infinite space, then the normalization constant of its wave function should be 0, because here is the normalization condition. Integral over volume, wave function squared, modulus squared, is just modulus squared of this normalization constant a times the volume of the infinite space. A squared times infinity, infinite volume must be 1, so a squared must be 0. So the wave function must be 0. That is, the wave function of a free electron is no wave function at all, no electron, but this is not what we need. The trick that we make is to consider an electron not in an infinite space, but in a cube of finite side length L. This number L, the side length of this cube, can be any big number, for example, 1 kilometer or 1 light year. And we impose, now we need to talk about the boundary conditions. What happens when the wave function of the electron reaches the boundary of the cube? What happens at the boundaries? And two things may happen. Either the wave function can be reflected by the boundary, or it can periodically repeat itself. So every time the wave function reaches the boundary, it periodically repeats itself on the opposite side of the cube. So that this would mimic the unconstrained motion of the electron. So, for example, the electron is described by a plane wave moving in the horizontal direction. Here is the boundary of the cube, and when the electron reaches that boundary, the wave function repeats itself on the opposite end. So this mimics the unconstrained motion of the electron in the horizontal direction. Now, mathematically, this periodic repetition of the wave function can be expressed by demanding that if you change any of the three space arguments of the wave function, x, y, or z, by the side length of the cube, L, the wave function does not change. Here, these are the periodic boundary conditions. And these periodic boundary conditions imply that the allowed values of the wave vector, k, must be 2 pi divided by L times a unit vector n, sorry, not a unit vector, times a vector n, whose all components are integer numbers. So nx and y and nz are integer numbers. Then it can be like if you plug in this expression for k vector into the original plane wave function and replace, for example, x with x plus L, you will find that the wave function gets multiplied by a factor exponential to the power I, imaginary unit, times an integer multiple of 2 pi, and exponential to the power I times an integer multiple of 2 pi is 1 by Euler's formula. It is cos of integer multiple of 2 pi, which is 1. All right, so these are the periodic boundary conditions. And then, after all is said and done, after all the calculations which involve this plane wave function are performed, we will take the limit L goes to infinity. And it turns out that the result is independent of the size of the cube. All right, so now that we are focusing on the cube of large but finite side length, the volume available to the electron is finite, it is L cubed, and the normalization constant is given the normalization constant squared times the volume L cubed must be 1, as follows from this normalization condition, which means that the normalization constant is an integer number, is 1 divided by L to the power 3/2. And in the numerator, we can have exponential, any number which whose modulus squared is 1. So exponential to the power I phi is a number whose modulus squared is 1, where phi is arbitrary. Now, but because the phase of the wave function is not measurable, we will follow the usual convention and say that phi equals 0, but we do not have to. Phi can be any number, any phase constant. All right, so now that we have this wave function of a plane wave written like this, the normalization constant is 1 over L to the power 3/2 times exponential to the power I k r minus omega t. We can start working on the differential equation that this function satisfies. Oh, and by the way, one more piece of information. So this normalization constant, 1 over L to the power 3/2, it is valid in 3 dimensions only. In 2 dimensions, this would be 1 divided by L. The electron is confined to a square of side length L, right? And in 1 dimension, it will be 1 divided by square root of L, where the electron is confined to a very large line of side of length L with periodic boundary conditions. So psi of x plus L is psi of x. All right. So back to our wave function written as a plane wave expression here. We know that the energy of the, how can we extract the energy of the electron from this plane wave? The energy is encoded in the phase of the electron. Kr minus omega t is the phase. And the phase is unmeasurable. I said that. But the rate of change of the phase in time or in space is measurable. This may seem a little bit contradictory. So you cannot measure the phase of the wave function, but you can measure how fast the phase changes in space or in time. But actually, the situation is already familiar to even the first-year physics students who have learned that the potential energy is not measurable, but the rate of change of the potential energy in space is measurable, and actually the negative space derivative of the potential energy is the force produced by this potential. So you have already seen this situation where you cannot measure some quantity, but you can measure how fast this quantity changes. Or even simpler situation, like you can, if you see a car on the highway, you can measure how fast it moves, but you cannot measure the distance it has traveled from start, because you do not know where that start happened, at which position the car started its motion. You can only measure the velocity. So it's there is nothing mysterious and nothing contradictory about saying that the phase of the wave function is not measurable, but the rate of change of the phase is measurable. All right, so how can we extract the energy from this plane wave function? Well, the energy is sitting in the angular frequency omega. And the angular frequency omega is related to the kinetic energy of the free particle by this Planck-Einstein relation. Namely, energy is Planck's constant times frequency, h bar times angular frequency, or h without a bar times the regular frequency f. Okay, so to extract the energy, we need to extract the frequency, angular frequency, from the wave function. And how do we do that? Well, by differentiation. If you differentiate the wave function, you are differentiating this exponential, and the derivative of an exponential is the same exponential multiplied with whatever multiplies the argument with respect to which you are performing your differentiation. So, and what multiplies the time argument t? Take the partial derivative of this wave function with respect to time. What multiplies this argument t? Well, angular frequency, omega, imaginary unit I, and there is a minus sign right here. So minus I omega psi. Now, if we use Einstein's relation between the angular frequency and energy, we find that we can replace omega with energy divided by h bar, and we find that the energy, kinetic energy of a free particle multiplying its wave function can be expressed as imaginary unit I times the reduce Planck's constant times the time derivative of the wave function. Notice that I am using the partial derivative d by dt instead of the regular derivatives because the wave function depends on 4 arguments: position, x, y, z, and time, t. So the derivative of a function of several variables is a partial derivative with respect to one of those variables. Now, what about momentum? For momentum, we need to recall the de Broglie's relation between momentum and the wave vector. So momentum is reduced Planck's constant times the wave vector. Why? Because the wavelength, lambda, is 2 pi divided by magnitude of the momentum. So momentum is, the wavelength is related to moment. So, sorry, the wavelength, lambda, is Planck's constant divided by the magnitude of the momentum. Okay. So momentum is Planck's constant h divided by the wavelength. Now the wave number is 2 pi divided by lambda, and Planck's constant h divided by 2 pi is h bar, reduce Planck's constant. The direction of the momentum, so the magnitude of momentum is reduced Planck's constant times the magnitude of the wave vector, and the direction of the momentum vector is the same as the direction of the wave vector k. So, hence this formula. Now, how can we extract the wave vector from the wave function? Well, by differentiation with respect to space. Actually, we have 3 derivatives to perform with respect to x, y, and with respect to z. And each of those 3 derivatives will result in the multiplication of the wave function by imaginary unit times either the x or y or z component of the wave vector. Each of those components of the wave vector is the momentum component divided by Planck's constant h bar. So now, just like we can combine the 3 components of the momentum vector px, py, pz into a single vector p, we also can combine the 3 partial derivatives with respect to x, y, and z into a single vector called nabla or gradient. So it is a vector operator whose all 3 components had partial derivatives with respect to x, y, and z. And then we obtain that the product of momentum vector and the wave function in a plane wave, written here, can be expressed as negative I imaginary unit times h bar times gradient of the wave function psi. The next piece of information is now we need a 3rd piece of information, namely the relation between the energy, which is related to the time derivative of the wave function, and the momentum, which is related to the space derivative, the gradient of the wave function. This relation is the usual energy-momentum relation for a free particle. Energy is momentum squared divided by twice the mass of the free particle. Now, we know how to extract the energy, but here we have from the wave function by differentiation with respect to time and multiplying the result with I h bar. But on the right-hand side, we have momentum squared times psi. Now, momentum squared is not a vector, it is a scalar, which equals to the sum of squares of the x, y, and z components of the momentum. So p squared is px squared plus py squared plus pz squared. Px squared, py squared, and pz squared can be extracted from the plane wave function here by differentiating it with respect to x, y, or z twice. And or in other words, you apply the momentum operator negative I h bar gradient 2 times. So if you apply gradient twice, that is the dot product of the gradient operator with itself is a scalar operator, which equals to the sum of second derivatives with respect to x, y, and z, and it is called the Laplacian operator. So momentum squared multiplying psi is negative h bar squared times Laplacian psi, gradient squared psi, where gradient squared or Laplacian is defined like this. So combining this expression for p squared psi and this expression for e psi in terms of p squared psi, we finally obtain the celebrated Schrödinger's equation for a free particle. I h bar times the partial time derivative of the wave function equals negative h bar squared over 2m times Laplacian of the wave function. So, like I said, we started with the solution, with the expected solution of this Schrödinger's equation, which is the plane wave solution right here. And based on that solution, and the relation between energy and momentum, we were able to construct a partial differential equation describing the wave function of a free particle. The plane wave solution that we started with, this one, is not the most general solution of the time-dependent Schrödinger's equation. This is the time-dependent Schrödinger's equation. Later we will introduce another version of Schrödinger's equation, time-independent Schrödinger's equation. Now, the time-dependent Schrödinger's equation has a plane wave as one of its solutions, but this plane wave solution is not the most general solution of the time-dependent Schrödinger's equation. Schrödinger's equation is a linear equation, which means that the sum, or a sum of any two solutions of this time-dependent Schrödinger's equation is also a solution of the time-dependent Schrödinger's equation. So any linear combination of plane waves like this will be a solution of this time-dependent Schrödinger's equation. So 1 divided by L to the power 3/2, A1 times exponential ik1r minus omega 1t plus A2 exponential ik2r minus omega 2t plus and so forth is the most general solution of this time-dependent Schrödinger's equation. 1 over L to the power 3/2 is therefore normalization. The parameters A1, A2, and so forth are the amplitudes of the partial plane waves which enter the solution. And now you can say, hold on. The momentum of the particle is h bar times the wave vector of the particle. The energy of the particle is h bar omega, angular frequency of the particle. But now we have several contributions, several possible wave vectors, several possible frequencies. And of course, the wave vectors and the frequencies in each of these partial waves must be related by the energy-momentum relation of a free massive particle. So energy is momentum squared over twice the mass. So frequency is wave vector squared divided by 2m h bar. H bar should be in the numerator. Sorry. All right. So this relation must hold. The energy momentum relation must hold for each partial wave. But now we have several partial waves entering the state of the particle. So let's say one partial wave propagates to the left, one propagates to the right. Where does the electron move? To the left or to the right? What is the momentum of the electron? H bar K1, H bar K2, H bar K3. What is the energy of the electron? H bar omega 1, H bar omega 2, H bar omega 3. What is it? And the answer is all of these values can be determined if you perform the actual measurement of the momentum or energy. Here is what happens before a measurement. Now, how can you measure the electron's momentum, for example? You can try and determine that, for example, the magnetic field produced by the electron. The electron is charged particle. We all know the Biot-Savart-Laplace law, the magnetic field produced by a charged particle moving with a particular velocity. So by measuring the magnetic field produced by the electron, you can determine its momentum. And when you perform this measurement, you will get only one of these momentum values, which is h bar k1, h bar k2, h bar k3, and so forth. Only one of those, of this set of values, which is found in the original wave function. But before the measurement, all these values are present in the wave function. In a sense, the electron moves simultaneously to the right and to the left. It has all possible momentum values which are encoded, which are present in its wave function. But a measurement will reveal only one of those values. And once the measurement is performed, the electron's wave function will, at the moment of the measurement, the electron's wave function will collapse to only one and momentum value, K1 and omega 1, for example, multiplied with h bar. And after the measurement, the wave function will remain in this single momentum, single energy state. Now, the probability that a measurement will reveal a particular value, let's say h bar kn, of the electron's momentum, is the modulo squared of the coefficient an, which multiplies the respective plane wave found in the wave function. So that's all about the time-dependent Schrödinger's equation. And next time, we will do the time-independent version. And for now, thank you all very much for your kind attention.